2D Echo. Basics of Echo. Outline. Introduction.
The piezoelectric effect in ultrasound.
Principles of Doppler. Introduction. The technique of using ultrasound to examine the heart is known as echocardiography or simply echo. Principles of ultrasound. Sound is a mechanical disturbance produced by passage of energy through a medium which may be gas, liquid or solid. Every sound has a particular frequency, a wavelength, its own velocity, and an intensity. Sound energy is transmitted through a medium in the form of cycles or waves. Frequency of sound is the number of times per second. It is expressed in cycles per second or hertz. Frequency is appreciated by the listener as pitch of sound. Wavelength is the distance traveled by sound in one cycle of rise and fall. The length of the wave is the distance between two consecutive peaks. Velocity is equal to frequency multiplied by wavelength. Intensity of sound, the loudness, or amplitude expressed in decibels. The normal audible range of sound frequency is 20 Hz to 20 kHz. Electricity and ultrasound are transformed from one to the other by special crystals made of ceramic such as barium titanate. Ultrasound relies on the property of such crystals to transform electrical current of changing voltage into mechanical vibrations or ultrasound waves. This is known as piezoelectric pressure electric effect. The piezoelectric effect in ultrasound. Electrical oscillation, crystal vibration, transmitted ultrasound, reflected ultrasound, crystal distortion, returning signal. When electrical current is passed through a piezoelectric crystal, the crystal vibrates. This generates ultrasound waves which are transmitted through the body by the transducer which houses several such crystals. Most of these ultrasound waves are scattered or absorbed by the tissues without any obvious effect. Only a few waves are reflected back to the transducer and echoed. Reflected ultrasound waves again distort the piezoelectric crystals and produce an electrical current. These reflected echoes are processed by filtration and amplification to be eventually displayed on the cathode ray tube. The reflected signal gives information about the depth and nature of the tissue studied. Most of the reflection occurs at interfaces between tissues of different density and hence a different echo reflectivity. The magnitude of electric current produced by the reflected ultrasound determines the intensity and brightness on the display screen. On the grayscale, high reflectivity from bone is white, low reflectivity from muscle is gray, and no reflection from air. Echo, reflectivity of various tissues on the grayscale. Tissue, reflectivity, shade, bone, high, white, muscle, low, gray, air, nil, black. The location of the image produced by the reflected ultrasound depends upon the time lag between transmission and reflection of ultrasound. Deeper structures are shown on the lower portion of the display screen, while superficial structures are shown on the upper portion. When ultrasound is transmitted through a uniform medium, it maintains its original direction but gets progressively scattered and absorbed. The wavelength of sound is the ratio between velocity and frequency. Wavelength is equal to velocity of frequency. High-frequency probes, 5.0 to 7.5 MHz, provide better resolution when applied for superficial structures and in children. Low-frequency probes, 2.5 to 3.5 MHz, provide better penetration when applied for deeper structures and in adults. Transducer, upper screen. A. B. Lower screen. Transducer is at the apex of visual display. A. Right ventricle in the upper screen. B. Left ventricle in the lower screen. Principles of Doppler. The Doppler acoustic effect is present and used by us in everyday life, although we do not realize it. The pitch of the horn sound is higher when it approaches you, higher frequency, than when it goes away from you, lower frequency. The change of frequency, Doppler shift, depends upon the speed and the original frequency of the sound. Ultrasound reflected back from a tissue interface gives information about the depth and echo reflectivity of the tissue. On the other hand, Doppler utilizes ultrasound reflected back from moving red blood cells, RBCs. The Doppler principle is used to derive the velocity of blood flow. Flow velocity is derived from the change of frequency that occurs between transmitted, original, and reflected, observed, ultrasound signal. The shift of frequency, Doppler shift, is proportional to ratio of velocity of blood to speed of sound and to the original frequency. For Doppler echo, maximum velocity information is obtained with the ultrasound beam aligned parallel to the direction of blood flow being studied. In the sharp contrast to conventional echo, where best image quality is obtained with the ultrasound beam aligned perpendicular to the structure being studied. There is a direct relationship between the peak velocity of blood flow through a stenotic valve and the pressure gradient across the valve. When the valve orifice is small, blood flow has to accelerate in order to eject the same stroke volume. This increase in velocity is measured by Doppler. Velocities towards the transducer are displayed above the baseline, positive deflection, and velocities away from the transducer are displayed below the baseline, negative deflection. The returning Doppler signal is a spectral trace of velocity display on a time axis. The area under curve, AUC, of the spectral trace is known as the flow velocity integral, FVI, of that velocity display. The value of FVI is determined by peak flow velocity and ejection time. It can be calculated by the software of most echo machines. When blood flow is smooth or laminar, most RBCs travel at the same velocity, since they accelerate and decelerate simultaneously. The spectral trace then has a thin outline with very few RBCs traveling at other velocities. This is known as low variance of velocities. When blood flow is turbulent as across stenotic valves, there is a wide disturbance of RBC's velocities and the Doppler signal appears filled in. This is known as high variance of velocities, spectral broadening, or increased bandwidth. The intensity of the Doppler signal is represented on the gray scale as darker shades of gray. Maximum number of RBCs traveling at a particular velocity cast a dark shade on the spectral trace. Few RBCs traveling at a higher velocity cast a light shade. This is best seen on the Doppler signal from a stenotic valve. The spectral display is most dense near the baseline, reflecting most RBCs moving at a low velocity close to the valve. Few RBCs accelerating through the stenotic valve are at a high velocity. The Doppler echo modes used clinically are continuous wave, CW, Doppler, and pulsed wave, PW Doppler. In CW Doppler, two piezoelectric crystals are used, one to transmit continuously and the other to receive continuously without any time gap. CW Doppler cannot precisely locate the signal, which may originate from anywhere along the length or breadth of the ultrasound beam. PW Doppler, a single piezoelectric crystal, to first emits a burst of ultrasound and then receives it after a preset time gap. The rate at which pulses are emitted is known as the pulse repetition frequency, PRF. Doppler signal across a stenotic aortic valve. A. Most RBCs moving at low velocity. B. Few RBCs moving at high velocity.
The maximum valve of Doppler frequency shift that can be accurately measured with a given pulse repetition frequency, PRF, is called the Nyquist limit.
The inability of PW Doppler to detect high-frequency Doppler shifts is known as aliasing.
Aliasing occurs when the Nyquist limit is exceeded.
Aliasing is an artificial reversal of velocity and distortion of the reflected signal. The phenomenon of aliasing is called a wraparound.